make the methods essentially more complicated in order that in one way or another they can take account of, or they can fairly reflect the genuine complexity of the social process that they're looking at. So complex analytical methods in one way or essentially another more complicated in order that in one way or another they can take account more fairly reflect, or they can fairly reflect the genuine complexity of the social process that they're so very often, and that's the theme. So complex analytical methods in one way or essentially more complicated in order that in one way or another they can take account variables, a multivariate approach, taking account of more measured things about people. But there are also other features of more complicated analysis, different approaches to modeling, and other forms of statistical summary. And in general, this is a bit of a challenge actually for people interested in using social statistics to tell stories about social processes, because kind of by definition, complex analytical methods are harder to know about. They're not as routinely taught on introductory courses. They go off in all sorts of different directions. There's all sorts of different things that you can try and learn about. They're harder to work with and harder to get on top of. So fewer people are as confident of making good use of more complex analytical methods, but arguably we would feel that the more complex methods are more appropriate in most situations for summarizing the relevant processes. So how do we go forward in a sensible way? So certainly this webinar series, we're trying to encourage people involved in the third sector in Scotland in particular, undertaking research to consider using statistical methods and consider using appropriate statistical methods, which might mean quite complicated statistical methods. What are the options when we don't have a lot of training to begin with? Well, there are plenty of resources out there that are available to prospective researchers to take them forwards in finding out about particular examples of advanced techniques of statistical analysis. Highlighted on screen, for example, just what happens to be the next things in line on the National Centre for Research Methods website. Some courses going on around about now on different examples of advanced statistical methods and advanced analytical methods in general. A challenge in keeping up with advanced methods is not only that are they more complicated, and we can typically think of what I mean by advanced methods here as things that aren't usually taught in basic training. They're more complicated. They're often emergent as well, in the sense that people are still working on their methodology. People are coming up with new software, new tools of analysis, new proposals of the optimal way to work to set up these forms of statistical analysis. And as I suggested before, a characteristic of advanced and emerging methods of analysis is that they're associated with attempts to take account of more variables in the process in one way or another. So what we thought we'd do in this webinar session, having introduced the idea that there are all these other techniques of analysis, or there are these more complex methods of statistical analysis that people don't widely know about, but that are out there and can be helpful. Well, we thought we'd pick out a handful of examples of advanced and emergent methods of statistical analysis that involve using lots of variables, and try and very briefly say a little bit about a bunch of them in ways that are potentially useful to a practitioner that hasn't done much previously with in this area. So what we're going to try and do, what I'm going to try and do, is run through some technical jargon, terminology, particular approaches to statistical analysis in the social science context that are developing at the moment, and that are thought in general to fall into the category of advanced and difficult things to learn about. For anybody interested, there are plenty of opportunities to follow up on these by attending free training courses or downloading training materials online in more depth in all sorts of contexts. So I would start that summary by mentioning GLMs, which may or may not already be familiar to those of you used to thinking about statistical analysis. We have had GLMs for a while, since the 1970s in this terminological framework, but they continue to be developed as tools of analysis and be important contributions to studying society. GLM stands for Generalized Linear Model, and all it really refers to is using devices known as statistical models in order to focus on telling a story about how a number of different explanatory factors might influence an outcome variable, a particular outcome variable. A convention we very often use in social statistics is to suggest an outcome variable might be labeled Y, and there may be a number of different explanatory variables, X variables, that all have an influence on Y. And a good way of describing how the X variables relate to Y is a statistical model that takes account of all of their influences in a combined way, models the joint relative effects of all of them on the outcome. Now, we've had statistical models for a long time. The earliest statistical models work very neatly when the Y variable is a numeric value, a continuous numeric value. But one major problem in social statistics is that many of the outcomes we're interested in aren't simple numbers. They're not numeric linear numbers. So if I focus, for example, on a volunteering measure, frequency of volunteering over the last 3 or more contacts in the BHPS. This is the one I mentioned before, where a small number of people, 2/3 or more of the time points in which they were interviewed, they were engaged in regular weekly volunteering. Lots of people never in any of the time points they were interviewed were engaged in volunteering, and there's a few more people in the middle. This isn't a straightforward number. We can't really give these categories the scores 1, 2, 3, 4 in a particularly meaningful way. So we need some sort of device to convert that into a format that will suit a statistical model, and that's what GLMs contribute. Generalized linear models are an approach to respecifying nonlinear outcome variables in a way that we can put them into a statistical model where the outcome in some meaningful way is modeled as a function of a number of explanatory variables. So we're looking at an outcome variable with 4 different categories and a different distribution in all those categories. One way that that could be modeled in the GLM framework is treating it as what's known as an ordered logit model, running an ordered logit model. And here on screen, I've got some parameters that come out from running a statistical model, an ordered logit model, a GLM model, on this particular outcome in the BHPS. And basically what these parameters show is the average influence of explanatory factors, net of each other, controlling for each other, upon being further along the ordered scale in this outcome variable. So we have a positive coefficient for a variable called fem, which is a dummy variable to indicate if somebody's female. The fact that it's positive means that people who are female, on average, are further along the ordered scale than people who aren't female. We've also got some information that it's statistically significant, that in this particular model software convention, the stars indicate that this is a statistically significant effect. So we're reasonably convinced that there's a genuine population level pattern whereby on average, net of age and other factors that we've controlled for, women on average are further along the ordered scale than men. And the attraction of the generalized linear modeling framework in general is that we can readily fit this sort of multivariate model where we've got a number of different explanatory factors as influencing an outcome of interest, and we can assess the distinctive effect of gender controlling for differences of, well, the other variables here represent age, cohabitation status, employment status, and a score for education level, number of children in the household, health status as well we've put in here. So the distinctive effect of gender after controlling for age, marital status, etc. comes out as positive significant. And that's a more powerful explanatory story than if we just did a two-way correlation between gender and volunteering behavior. The statistical models in general are very useful devices for telling us about the effect of X variables on Y variables. And the key thing to know about generalized linear models is that they open up the avenues for fitting statistical models to a much wider range of situations, all sorts of different forms for the outcome variable Y. So we've got GLMs. We've also got something called GLMs in social statistics. So these essentially can be thought of as generalizations of the generalized linear model, extensions of the generalized linear model that allow it to take account of other things in addition, other complexities to the data structure typically, other features of the variables involved in the analysis. So GLMs were basically a regular statistical model, but allowing for the possibility of the y variable to take all sorts of different structures. GLMs allow for the possibility that the y or the x variables might actually be latent variables rather than real variables. And latent variable basically means they're a concept that we don't have a direct measure of, but we have a measure of something else that we expect is related to that concept. And mixed models, well, this refers to a particular feature of the modeling design, something we'll come back to later in the webinar, actually, talking about multi-level models. But mixed models are specifications about the error terms in statistical models that allow us to take account of other complexities about the data, such as complex sampling structure and so forth. So this particular GLM output that I'm showing is produced by using the software Stata again. For the same model that we were looking at on the earlier slide, it's an ordered logit regression looking at the volunteering engagement over time outcome with a bunch of explanatory variables, but we've got some additional controls in the GLLMM taking account of clustering of the data, in this case, into primary sampling units. It's a complicated survey data set with additional clustering factors. So we have GLMs, which are models in a variety of situations, and then GLLMs allow us to more appropriately apply GLMs really in more complex data scenarios. A different advanced and emerging aspect of doing statistical analysis with lots of explanatory variables. Possibly you may have heard of people talking about marginal effects when summarizing the results of statistical models. In my opinion, this is something that's really taken off in the last decade or so in social statistics across social science disciplines. Essentially, thinking about marginal effects refers to paying more attention to giving appropriate summaries of the distinctive effect of one X variable upon an outcome in the context of other factors in the model. One of the things about using statistical models as ways of describing patterns in data is that the effect of any one factor, explanatory factor, will be contingent upon values and circumstances of other explanatory factors in many data scenarios, certainly whenever the outcome variable y is nonlinear in form. So there's been quite a lot of work in social statistics about trying to come up with devices and procedures to more appropriately summarize the distinctive effect of a change in the values of the x variable upon the outcome variable, and marginal effects is one way of representing that. They essentially refer to predicted values of the y variable contingent upon all the other variables in the model and in contrast to different values of the key x variable. So the graph here is a graphical presentation of marginal effects as influences upon, in this case, volunteering, predicted probability of regularly volunteering in this same BHPS data set. And we've got some values that show the average predicted probability for men and women, whether they're in work or not in work. And this is conditional on all the other variables in the model. And the point is that these particular values are interpretable. The predicted probability is quite a useful value to have. It's not exactly the same as we were seeing in the model and the original model parameters. So these predicted probabilities don't emerge directly from the original model parameters, but some background calculation work needs to be undertaken to come up with suitable marginal effects, predicted probabilities, differences in predicted probabilities in this context. So one of the advanced and emerging aspects to using statistical analysis in a modeling framework with lots of different explanatory variables is a tendency in social statistics to pay more extensive attention to the appropriate summary of the distinctive effects of one particular explanatory variable in the context of others through using marginal effects. A different point that's worth making about, again, advanced and emerging approaches to statistical analysis is the role of model comparisons in most examples of more complicated statistical analysis when we're trying to assess the effects of lots of different explanatory variables on an outcome. One way to understand statistical modeling perhaps is to think of the actual data in the variable by case matrix as the product of the model fit and an error term, which is the difference between what's predicted for an outcome under the model and the actual observed outcome for any particular case. And the idea of using a statistical model is that we get a model that gives us a model fit that is getting to be reasonably close to the data, or at least that minimizes the error in the data. And statistical modeling is used really a great deal to tell stories about complicated patterns in data. What we normally do is build up a series of model comparisons where we set up a series of different statistical models with small differences between them, perhaps with more and fewer explanatory variables, perhaps with other constraints in some models and not in others. And we evaluate which of the different models is preferable by some agreed criteria. Traditional social statistics in most situations could be characterized as what's sometimes known as frequentist social statistics, where we essentially what we're doing in model comparisons is we're trying to find the best fitting model from a range of different possibilities, the one that comes closest to the data and also is reasonably parsimonious. Parsimony in statistical model refers to a model setup which is both close to the data but also using as few explanatory variables as is sensible, as is reasonably possible. What we don't want to do is add in loads of extra terms to the model which don't really change the model fit or the model circumstances. Parsimonious model gives a good description of the data without using too many extra parameters. So in the frequentist tradition, we usually set up a few different models, compare them, try and identify the most parsimonious one. In the output that I've got on the screen, I've got two different models from SATA in the SATA software, and I've got the average effects of some explanatory variables on the volunteering outcome in the first model, Logit 1, and I've added a couple more explanatory variables in Logit 2. And I've got two different models. I can compare the relative fit of the model. The things that are circled here are various statistics that can tell us about the relative fit. But one important statistic is BIC, or the Bayesian Information Criteria. And basically, this is a number that relates to how well the model fits with the data. And the lower value of BIC would tend to indicate the more parsimonious of the models. In this particular model comparison, Logit 1 would typically be regarded as the better model because it has much the same explanatory power as Logit 2, but it uses less parameters, so it's more parsimonious. And that can be seen from the lower BIC value, for example. Now, in model comparisons, frequentist statistical traditions, which are essentially most social statisticians, frequentists would look at different models and try and identify the optimal one, the one that comes closest to the data, and focus on that and its particular estimated values. There is another tradition in model comparison in social statistics that you might sometimes hear about in advanced literatures. The Bayesian statistical analysis tradition has a number of differences from the frequentist tradition in how it tries to characterize statistical results. Most importantly, in the Bayesian tradition, a statistician wouldn't be trying to identify one single optimal model in most cases, but they'd be trying to give a sense of a distribution of plausible model and model parameters, which are all a decent fit to the data or are reasonably close to the data. And they also, in the Bayesian tradition, there may be an argument for putting in what's usually referred to as prior input or priors to the data. So that's essentially pre-specified views about what the appropriate parameter values are in the statistical model. So a statement in advance of what the value is likely to be. But the Bayesian tradition would try and get away from the point estimate approach that's associated with the frequentist tradition of finding a particular single best value for a single best model or single best model parameter, but instead we're trying to convey a distribution of plausible values given the statistical patterns in the data. So it gets complicated, of course, but most of the work, the point I'm trying to make here is that most of the work of statistical analysis is usually achieved by setting up different statistical models for the data and making comparisons between them in some way. Now, 2 more points about advanced and emerging aspects of statistical modeling are about causality, which at one point was a dirty word in social statistics. Many of you, perhaps with classical training in statistics, will have had it drummed into you. I certainly did when I first learned about social statistics, that statistical patterns are associations but not causation indicators. If you find a correlation between 2 things, that tells you they're associated. It doesn't necessarily tell you that one causes the other. That became quite a conventional orthodox position in social statistics, but some people say that in the last decade or so, we've taken a causal turn in approaches to summarizing statistical data. Suddenly people in social statistics are trying to do things that attempt to make reasonable claims about causation. The premise here is that ideally, if we could, as social scientists, we would like to make statements about causation. We're well aware that data patterns don't necessarily prove causation, but the idea is that maybe with sufficient depth of controls in the data, it is conceivable that statistical patterns that we get out after controlling for lots and lots of other things might actually genuinely be things that could tell us about causal patterns after all. Now, there's a few different ways the causal turn can be approached. One of the influential examples is a type of statistical model known as the fixed effects model. And it does rely on a certain type of data. It relies on longitudinal panel data, at least in the context that I'm describing it. And the idea of the fixed effects model, if we've got panel data where we've got multiple records from the same people at different points in time, the idea is you can control for all the other influential factors in statistical patterns by having controls for people themselves, essentially, because you've got multiple records from the same people. Therefore, if you focus on differences in responses for the same people, you're controlling for all the things about people that are about themselves. You also have controls for other population level differences in patterns over and above controls for the people themselves. And on top of all of that, the idea is that we've got a sufficient depth of explanation that we really maybe are genuinely talking about underlying causal patterns in the data. Now, the output that I've got on the screen here is the output from 2 different regression models on the same thing. What I'm looking at here is subjective well-being, GHQ, and a higher GHQ means worse subjective well-being. And I'm looking at the effect of volunteering along with other explanatory factors upon subjective well-being. The first model is just essentially a regular regression. It's actually a population average panel model, but it equates more or less to a regular linear regression. And we've got a negative significant coefficient for the effect of volunteering on GHQ. Basically, if you volunteer compared to if you don't, you're likely to have a lower GHQ, i.e. you're somewhat happier, better subjective well-being. That would be good news, we'd think, in many situations. But this is just across all the different data points in the survey. It doesn't really control for differences between people. So maybe people who are happier are more inclined to volunteer anyway. And maybe that means that this coefficient is a rather biased representation of the effect of volunteering. Now, what the fixed effects panel model would do, the second column in this table, is it would focus on how changes in volunteering behavior within people influence changes on GHQ behavior within people, with other controls as well for other measured things about people. So we get a different coefficient, a smaller but still negative and significant coefficient coming out of this model. And that's telling us that on average, the impact of the same person moving from not volunteering to volunteering on average comes out as a GHQ reduction of 0.25. But in this second model with the fixed effects, not only would we maybe believe that this is an association with GHQ, volunteering is associated with a reduction in GHQ, we might even believe this is compelling evidence of a genuinely causal effect, because we've controlled for so many things that there's hardly any other reasonable explanation for this statistical pattern other than causality. So the first model would just tell us that there's an average pattern of connection between volunteering and GHQ. The second model might genuinely make us believe that there really is a causal effect, that when somebody volunteers, it reduces their GHQ, it makes them happier by a magnitude of 0.25 on average. So the causal turn in social statistics is quite consequential because it gives us more powerful results if we believe it. And there is another influential category of causal analysis that I'll just describe without an example, but just in how it works. And that's using what's often known as the counterfactual model. Now, the counterfactual model in causal analysis is an attempt to say something about the difference between the actual observed outcome for any individual unit and the outcome that would have happened to them in the counterfactual scenario. So it's an impossible situation in itself, but what you try and do is come up with a statistical approach that mimics it. So the counterfactual approach to causal analysis would be to say that if you want to understand the causal effect of volunteering, what you need to do is have two different data points, which actually you can't simultaneously have. So if we think of Dave, who does some volunteering, we want to know what is his well-being given that he volunteers, and at the same time, simultaneously, what would, in a counterfactual sense, what would his outcome have been had he not volunteered at exactly the same time that he did volunteer, with everything else being the same. So it's impossible to do this. There are attempts to come up with statistical tools that come as close as conceivably possible to those counterfactual data points. And I'll just flag one method, propensity score matching, which has been written about a lot in recent years in sociology and other social sciences. What propensity score matching tries to do is to mimic the counterfactual model by going through large data sets with a lot of data about people. And what it tries to do is identify pairs of people who are identical in every respect, except that they don't have the key explanatory variable. They don't have the same values on the key explanatory variables that we're interested in. So here the key explanatory variable is whether you volunteer and its influence upon the outcome variable, which is subjective well-being. So what we essentially try and do is find Dave in the data set who does volunteer, and then we try and find another case in the data set who isn't Dave, but who is somebody who is identical to Dave in all sorts of other respects, or as close as identical as possible, and then we contrast their values in well-being. And is Dave happier than the other person who's just like Dave but isn't Dave, but is similar in all the other situations? And propensity score matching is a method of a statistical analysis that does this, or attempts to do this, and is often deployed as a device for making potentially causal statements about on the basis of statistical data patterns. So causal analysis, whether through the fixed effects model or through counterfactual models, something I would characterize as an advanced and emerging method of analysis. Three further brief points to make about advanced and emerging methods of analysis that make use of lots of explanatory variables. Complex surveys. So social surveys which have a lot of data in them, that have lots of explanatory variables, are invariably also complicated in other ways as well. They typically use a sampling design that isn't a simple random sample. They also, of course, they have differential response rates that mean that they're not simple random samples for those reasons as well. And it's quite complicated, but not impossible to deal with data about the complex sampling design and to build that into statistical analysis. This is actually a point we've made again in earlier stages in our webinar series. But generally speaking, if we have access to quite rich, complicated data resources, we can potentially use things like sampling weights, sampling factors, cluster controls, strata controls, for instance, to adapt the analysis, recognizing the imperfections or the complexities in the sampling structure. Now, the thing to know about this, about weighting and clustering and strata controls, is that what people do is not very consistent at all. I've said that it's neither normalized nor standardized, in the sense that different people have different habits of using weights in different scenarios, and there isn't really a single authoritative reference that tells people this is the one and only and best way to take account of complex sampling design. There's ongoing academic and statistical development of tools and approaches to taking account of complex data structures. Unfortunately, it's not a simple or straightforward thing to do, but it's a point to be aware of in endeavoring to engage with advanced and emerging methods of analysis. And two other things that it's worth flagging. One example of advanced and emerging data analysis that is actually people are often aware of are multivariate tools that try and take account of data from lots of different variables in some sort of data reduction device, where essentially they try and cluster cases into categories that are similar on a range of different variables, or maybe try and find underlying dimensions of differences between cases on the basis of lots of different explanatory variables. Something that got a lot of coverage in my discipline in sociology, something known as the Great British Class Survey, which was conducted partly through the BBC, but by academics as well, Mike Savage and colleagues, in their article summarising the work in 2013. What they did was essentially, it amounts essentially to a cluster analysis of data about lots of different features of individuals, things like their socioeconomic circumstances, their educational background, their social connections and social circumstances, things they do for leisure. And it tried to find categories of people based upon combinations of circumstances that are quite common. In this particular approach, they came up with a 7-class categorization for the contemporary UK. They argued that most people in the UK can reasonably be located in one of 7 latent classes. The one I'm showing on screen, emergent service workers, characterized by a number of different things, but they're typically young, they typically have cultured social life, but they mostly rent their own homes, for example. Lots of features about them that are, on average, are distinctive without applying necessarily to every single person in them. You might have heard of these sorts of clustering and data reduction tools because they're quite popular, particularly in market research and also in political research, trying to characterize categories of voter, types of person in terms of their attitudes or their outlooks. And these are a style of advanced method of analysis. People are still coming up with or trying out new devices for things like cluster analysis, latent class analysis. Again, they're not routinely taught in basic social statistics courses, but again, they're characterized by trying to use data from a lot of different variables at the same time. One last thing to flag, a different thing again, network analysis and analyzing data on social connections or connections between units. A different thing again as a statistical method, but I would highlight it again as an advanced and emerging technique of analysis that's characterized by using lots of data about lots of things. Network analysis is a bit different. Network analysis is about collecting data on connections between units, whatever the units are, people, firms. In the image I'm showing, the units are actually occupations. We've got data on whether or not there are social connections between occupations or disproportionately common social connections between occupations. We're looking at ways of summarizing data on those connections. So the image that I'm showing is something known as a sociogram, often used in network analysis, but by no means the only thing you can do with network data. There's various devices for statistical as well as graphical summary of links between units. In network data, we've usually got lots and lots of information because we've got connections between all the different units, information on whether or not there's a connection between all of the different relevant units. Plus, we've also typically got additional information about characteristics of the units. So the color coding in this image is about characteristics of the occupations in terms of the sectors and the levels of social advantage in the occupations. And the lines between them tell us whether or not those particular occupations have disproportionately common social connections between them. For instance, this is work summarized by my colleague David Griffith and I in an article on social connections between occupations. So hopefully that was an exhaustive and comprehensive account of everything that's advanced and emerging in social statistics in the world. An expression we sometimes use in social statistics is they're trying to be realistically complex. We know that the social world isn't simple, and it's not necessarily going to be satisfying to try and describe it in a simplified way. So we come up with statistical techniques that take a more full account of the complexities of society. But that comes with complications because these statistical techniques are more complicated, not as easily understood, not as widely taught. But the last thing to cling on to when talking about these methods is that there's loads of things out there online, free training courses in the UK, for example, all sorts of resources out there that can take you forward in learning about any of these particular techniques if that's the next thing that you want to do. Okay, so in the first of today's webinar sessions, I wanted to...
Our workshops and webinars have been designed with the aim of building capacity in third sector organisations to engage with data. We've focused on developing data skills and showing what resources and methods are out there and how they might be useful. In this session, I want to take a step back and look at an overview of the range of skills involved with analysing data to help you think about where you're at now and what sort of skills you might want to develop next. So we're going to look at how you can develop your data analysis skills. Data analysis involves a range of skills from collecting data, managing data, analysing that data, reporting and communicating on the analysis of data that you've done. It's a practical skill, but it involves some knowledge of the statistical methods that you might use to analyse, of social research methods. And it also usually requires some knowledge of software packages in order to be able to actually work with the data. Starting out, this can seem quite daunting. The sort of things that you might do to begin with are manipulating data, describing your data, and starting to look at relationships between different variables in your data. The analysis that people are most familiar with is measuring the shape and distribution of a variable. This is where we're calculating an average, a mean, a median, or mode, or perhaps we're thinking about the distribution, the range, or a measure of variability in the standard deviation. You might use histograms or bar charts to look at the shape of your data. The aim here is to describe what you've got and see what your data is telling you. Then you might start to look at relationships between variables, creating tables to cross-tabulate different variables or compare averages across groups. You might even get onto measures of association and correlation. How strong is the relationship between variables? And the practical skills you'll need to develop here are being able to open data files, being able to code variables, do a little bit of data cleaning to make sure it's in the right format, and you need to be able to document your analysis to be able to tell other people what you've done. So those are the basic data analysis skills when you're starting out. The next step is to try and draw inferences from the data that you have about a more general population. So you're looking at a sample, but you want to be able to say something about people or organizations that aren't in your sample. You want to be able to generalize what you're looking at. So the next step in methods is looking at how you do that generalization, how you make inferences about a population. And a key concept here is uncertainty and confidence intervals, being able to say something about how confident you are in the findings. There are a range of statistical methods that help you to make inferences about a population. And the objective here is usually to provide evidence of real effects, to be able to say whether a pattern that you see in the data you've collected is likely to be a pattern that's actually out there in the world. Here we engage a bit more with probability, with hypothesis testing, and being able to make claims that generalize from a sample to a population. A really important concept here is uncertainty. When you're generalizing from a sample, you need to be able to quantify that uncertainty. So you're likely to use confidence intervals to be able to put a range around the estimates. You then might compare those estimates and use those comparisons to draw conclusions about a population. Are two groups really different, or is it just to do with the sample that you've drawn? You'll also develop more advanced data management skills. You might need to derive variables, combining data from more than one variable to create another one. You might combine data from different files, combining or linking the data across different data sources. If you do more complicated analysis, you'll need to develop your workflow, how you keep a record of what you've done so that you make sure you can come back to it and do it again, or you can explain it to other people. And you'll need to keep better documentation about the analysis that you've done. And you may start thinking about sharing some of the data, and so being able to write documentation that's useful to other people. Once you've mastered these skills, then you're into the realms of thinking about more advanced quantitative methods and more advanced ways of working to analyze data. You're likely to want to think about more complex relationships involving several variables, and perhaps producing descriptive statistics or tables to describe those relationships. Perhaps you'll start doing some modeling, incorporating a number of variables in order to model a particular outcome. You can do more complicated multivariate comparisons using the sorts of methods you're already familiar with. So just producing more complex tables that have more groups or more complicated subgroups. Perhaps you're comparing averages across combinations of different characteristics. You might want to look at how relationships, the measures of association, differ between different groups. This uses the methods you're familiar with, but brings in more complexity by introducing additional variables. You may want to start modeling, thinking about one outcome being determined by a number of explanatory factors and taking them into account so that you can start to look at the impact of one variable after controlling for the impact of another. You might do relatively simple linear regression where you're modeling metric outcomes, or binary regression where you're looking at some categorical outcomes. Models allow you to really focus on an outcome of interest and take into account quite complex relationships between combinations of variables. More advanced modeling lets you think about causal analysis, actually trying to go beyond correlation into looking at causal effects. Methods here include instrumental variables and natural experiments that take account of random variation in order to get at causal effects. You might want to do longitudinal modeling, where you follow the same cases over time, whether individuals or organizations. These repeated observations help you understand change and also help you get at causality. Or perhaps you're modeling more complicated relationships and you want to use multi-level modeling, where there are different effects going on at different levels. For example, local authority, neighborhood, household, and individual levels. These more advanced methods need greater study, but they allow you to capture even more complex relationships between variables. As your analysis gets more complicated, you have to think more about how to communicate it to others, particularly if they're not familiar with the methods that you use. There's a whole field of data visualization, understanding how best to communicate quantitative findings. You might learn how to use a combination of graphs, charts, infographics, diagrams, or perhaps even get into producing dynamic or interactive visualizations that allow users to explore the data themselves and play with the complexity. All these methods together and more make up the range of data analysis skills that you might want to master. You can think about where you are in this process, what sort of skills you've already got, and what sort of skills might be useful to you in your role. Where would you like to get to? There's a wide range of training available, both formal and informal, from a range of organizations to help you develop data analysis skills in these areas. But if you're struggling to think which skill to acquire next or where you should focus on, think about this progression from moving from descriptive analysis to being able to generalize to a population, to trying to capture more complex relationships and think about causal effects. Think about where you are in that journey and where you want to go next.
Okay, so this is intended as a quick talk about multi-level modeling. Multi-level modeling is quite a popular technique of statistical analysis in the social sciences, but in this session I just want to outline what it is, what it means, and give you some pointers on how to go a little bit further finding out about multi-level analysis. The multi-level modeling in general refers to a style of statistical modeling with a particular purpose added to it. Stirling has the language of talking about parametric analogies, ways of drawing analogies about social processes through the devices of statistical parameters, specific statistics. Multi-level models I would describe as a special case of statistical models when we build into the models some account for structures in the data that essentially in some way involve clustering or hierarchical patterns or a nested relationship between cases. I'll say in a second what we mean by that. Multi-level models are quite widely known and used in the social sciences. In general, in the social science context, they also mean not just generically types of models that take account of clustering and nesting, but they mean a particular approach to doing that, something known as estimating random effects for the cluster structure. So there's a few different things you can do with clustered data, but generally speaking, when people talk about multi-level modeling in the social sciences, it ordinarily means specifically the random effects approach to dealing with the cluster structure. And also the traditional multi-level modeling in the social sciences is usually associated with scenarios where people are genuinely quite interested in the clustering structure and the patterns in the data. It's not just a control that they want to deal with, although sometimes that's what it is, but typically it's something a bit more than that, something quite interesting about the data pattern. So what do we mean by clustering, nesting, hierarchy? This graphical depiction hopefully makes it clear the sorts of patterns in data that we're talking about. A very common application area of multi-level modeling is in educational research, where we might have multiple records from different pupils, for example, but those pupils are clustered into classes or schools or something. And multi-level modeling generally refers to all sorts of scenarios where you've got records clustered within other units. This is what we'd call, depicted in this image, is what we'd call a two-level structure, the lower level and the higher level. But we can have more than two levels, and we can have more complicated relationships between different levels, in fact, in the data. Multi-level modeling would refer to some sort of adjustment to the analysis to take account of that clustering. If we start with a single level model without a multi-level account, what we do with a statistical model is come up with parameters that describe overall all the cases in the data, the average influences of explanatory variables on outcomes. In the case of multi-level modeling, we have clustering of records within units of some form, clustering of pupils in schools and so forth, and we want to build that information into the analysis in some sensible way. One possibility would be different models for different cluster units. So if we've got pupils clustered in schools, we could do a different model for each different school, for example, come up with different model parameters for each of the higher level clusters. Generally speaking, that's less appealing because it's too complicated. It'll come up with too many model parameters. What we'd rather do is have an improved overall average description which recognizes the structures in the data in some way. And this is what's usually done with the random effects multi-level models. So look at a quick example. A very well-known example, actually, something called the Junior School Project dataset, which is used in a lot of different methodological applications with multi-level models. It's an education data set. We've got data from 4,000 different pupils clustered into 65 different schools. And we'll look at some images in a moment which contrast a couple of different situations. A single model just for all of the pupils, ignoring the clustering in schools. A series of different models where we fit different regressions for each school. And then the third option, which is the random effects multi-level models, where we have an overall model, but we're sensitive to the different schools. And this image is trying to capture all of those things. The model that's been estimated is predictors of GCSE attainment, exam attainment at age 16. It's actually as a function of a number of different things, but we're concentrating on one of the explanatory variables. It's something called LRT, which is a reading test score. It's actually the reading test score of pupils when they're aged 11, and we're looking at how that's related to the GCSE score at 16. If we close our eyes to the clustering of cases within all the different schools, we could just fit a a single regression line to that overall structure. That's what I'm trying to indicate in the top left. Another possibility would be a different regression model for each of the different schools. Here I've plotted the regression slopes that we get from doing 65 different models. It's actually slightly less than 65 because we're not including the schools with less than 5 pupils in, but we've got a bunch of different regression lines for each of the different schools. On the bottom of the image, we've got some multi-level models using random effects. We've got two different types of models, random intercepts and random coefficients, and these are the two main categories of multi-level model that are often used in social sciences. Basically, in the random intercepts models, what we do is we allow for the possibility that from school to school, well, sometimes GCSE attainment is a bit higher and sometimes it's a bit lower. And we build that into the model, we come up with an overall model line, but we allow for variance from school to school around about the overall average. And random coefficients terminology usually refers to the scenario where it's not just that we allow for school to school variation in the overall level, but we also allow for the possibility of school to school variation in the gradient as well of any particular explanatory variable. So here we've got different slopes for different schools, still though within a unifying model, a single overall model, but we're allowing for the possibility of variation in the average influence of LRT from school to school. So it's some variation in the gradients there. So how do multi-level models with random effects work? Basically, the random effects part of the specification refers to what's normally known as decomposition of the error variance, if this means much to you. When we fit a multi-level model, a model in general, we have an outcome as a function of explanatory variables. So y equals beta x characterizes the relationship between a number of x variables and an outcome. There's a gap between the fitted model and the outcome, which is essentially the error term. For every individual case, there's a difference between the predicted value under the model and their actual observed value. That's the error. Usually we just leave that error alone. It's just a gap between the model fit and the actual data. But in the random effects type of multi-level modeling, what we do is we actually model variations in the error for any individual case, or for the cases as a whole. We say some of those errors are associated with higher level units. So here Ji would indicate the higher level the schools say, and Ij would be the individuals within the schools. So we decompose the error into a bit that's just about schools. If you're in school, Ji equals 1, you're a bit higher than average. If you're in school, Ji equals 2, lower than average. And another bit of error that's about variations from individuals to individuals, net of the school level pattern. Two common types of random effects model are used in the social sciences: the random intercepts model and the random slopes model. The random intercepts model is the simpler example that I was in the previous equation, where we just say if you're in one school or another, one cluster or another, your value goes up or down a little bit, the single higher level error term, the mu Ji. In the random coefficients, this is made a bit more complicated because we say that the school level error term, or the cluster level error term itself, could actually be different for different values of x variables. It's allowed to be a function of some of the x variables, the explanatory variables themselves. And actually, technically, although it's not usually used, the lower level error variables or error terms also could conceivably be a function of values of x variables. This sounds really complicated, but actually the interpretation of random coefficients is a lot easier than the representation through equations. So basically what we're saying with this specification comes out as being that the way in which explanatory variables work is a bit different from cluster to cluster. It's a bit higher in one cluster and in another cluster. And this is like the image we were looking at before, where we were saying the gradient of the effect of LRT in the education case was a bit steeper in some schools than in other schools. We're saying from school to school, from cluster to cluster, the impact of the x variable could be a bit bigger or a bit smaller. There are other scenarios where we can fit random coefficients terms that are sometimes helpful in multi-level models, but they typically have less of a useful substantive interpretation. as the particular scenario of fitting, allowing the effect of a lower level explanatory factor to be different from cluster to cluster. The random intercepts version, the simpler version of the random coefficients model, where the only thing we allow for is a flat rate increment or decrement from cluster to cluster in the outcome. We've just got this mu term, mu gi term. But in the random coefficients scenario, we say that that increment can actually itself be related to explanatory variables. It sounds really complicated, or I'm making it sound really complicated in how I'm describing it just now. But again, if we look at the actual data patterns that we're dealing with, it's perhaps easier to see what's going on. The random intercepts model, some schools are higher than others, they move up or down, but in a sense it's parallel lines, because net of that overall increment, there's no further change related to the X variable, the read and test score in this case. The random slopes, a random coefficients model, on the other hand, we're saying the slope itself can be different from cluster to cluster. It's allowed to be different from school to school in this case. Now, multi-level models with random effects nowadays can be fit quite readily in most standard software. Certainly SPSS and Stata and other general purpose software have facilities for random effects models. And at the simplest level, it's easy to think of random effects multi-level models as just regression with a tiny bit extra. A book by Bickel makes that point quite ardently, that multi-level models essentially equate to regression models just with that extra term. In the language of Stata, for example, this is the code to run a regular regression, and on the same data set, a multi-level model with clustering of records into classes, pupils in classes. Almost the same code, just a minor difference in specification. The mixed term to specify that it's a random effects multi-level model, and the pipe class indicated to say that the variable class indicates the cluster membership. Now, there is a lot of underlying complexity to the specification and interpretation of random effects models that I'm skipping over a little bit here. Not least the calculation of the random effects distributions themselves is not straightforward. There's different estimation algorithms available, and different algorithms actually tend to lead to different results. Often as well, multi-level models with random effects are quite hard to get to converge at all. The initial introduction is much simpler than the actual long-term implementation of them. They work in more complicated ways when you get into the details. But you can get started quite rapidly on multi-level models nevertheless. So here's a little example associated with data on volunteering, and it's actually a bit of work in progress that I'm developing with Alasdair Rutherford at Stirling. And we're interested in occupation to occupation variations in volunteering experiences. And our idea is that there could be processes related to individual occupations that influence volunteering experiences, whether people volunteer or engage in civil society activities at all, but also perhaps the benefits of volunteering. Could they be different from job to job? Now, in most data sets, we have quite a lot of different jobs measured, about 400 is typical in a UK data set. So we've got clustering of individuals into occupations, essentially. And what we're going to try and do is assess, are there distinctive patterns whereby outcomes that we're interested in are different from occupation to occupation? And it makes sense to use a random effects multi-level model here because we've got lots of different occupations. We wouldn't necessarily want to put dummy variables in for all of the different 400 occupations, but we would want to allow for those differences in some way in the analysis. So it's well known that volunteering behavior, propensity, or the experience of volunteering is related to other characteristics: gender, age, ethnicity, social class, social stratification, position. All of these are connected to volunteering patterns empirically on average. So our idea is specific occupations matter. And actually the image I've got at the bottom here is an empirical depiction of data that corresponds to that. What we're looking at is propensity to volunteer, how it's related to individual occupations. All these different points refer to 400 different occupations, and the lines are error bars, and basically when they don't overlap the zero line, we've got individual occupations that stand out as having above average or below average propensities to volunteer net of other characteristics that we've controlled for in the model. So this image is after running a random intercepts model where we allowed for the possibility of occupation-to-occupation variation in volunteering propensity, net of other factors controlled for in the model. And sure enough, we did find some occupations are higher or lower in their average volunteering patterns. So here it's a useful descriptive device characterizing empirical variations in things related to volunteering. One of the things we sometimes do with multi-level models is we calculate the model first, and then given the model results, we might want to pull out the cluster units that stand out as being at one extreme or another, the ones that are much higher average volunteering after controlling for other factors, or that are lower levels of volunteering than we might imagine. So Alasdair and I have been doing this in this paper, looking at volunteering in occupations, and in the UK data, and there's a few different scenarios, but if we just concentrate on the first one, here are some occupations that stand out in the UK context, net of controls for other things about people as having higher levels of volunteering than we might otherwise expect after controlling for other factors such as age and gender and other things that influence volunteering. Here are some occupations that have lower average levels of volunteering. Computer analysts, sales assistants, clerks, electricians, various types of job that maybe there's some feature of those jobs or circumstances of those jobs that mean people are less likely to volunteer than would otherwise be predicted on the basis of other characteristics about them, such as their age and gender and education level. So this is potentially interesting, useful descriptive information in this scenario achieved through a multi-level model with random effects. Can go on and on, of course, with multi-level models. One of the things we've been trying in our own analysis is looking to see how variations in occupations and their relations to volunteering patterns are different depending on how we measure volunteering and civil society engagement. So there's lots of different possibilities. One of the things we've actually got in the data are we've got some longitudinal data on repeated volunteering patterns. So the civic core, the idea of people who volunteer a lot and on a regular basis. And we've got data on volunteering from a number of different surveys, which has been summarized here. So I won't talk about all the details, but what we've got here are some summary statistics about the magnitude of occupation level variation. The bigger the number, the more of the empirical pattern is connected to occupations. So in many of these cases, in all the cases that are in bold, we're seeing significant empirical patterns of occupation to occupation clustering and volunteering propensities or experiences, net of other controls in the model. And this is interesting for us, compelling evidence to suggest that there are some things going on at the occupational level that we'd be interested in. So in the multi-level analysis, our higher level of occupations, and the random effects model gives us some empirical suggestion that there are things going on at the occupational level that are worth looking further at. Points I'm trying to make in this talk, multi-level models are a type of statistical modeling device that are particularly designed for taking account of clustering structure in data. Quite often clustering structure is genuinely substantively interesting. So in the last example, individuals clustered in occupations were really interested in what's going on with occupations. The basic setup of random effects multi-level models is fairly straightforward these days. It's available routinely on software packages, but it does get more complicated quite quickly. There are challenges of estimation and organization. But nevertheless, multi-level models are really quite handy tools of statistical analysis. They're used quite a lot in the social sciences. They're non-standard, more advanced methods of analysis, but they are used quite a lot. And it does seem to me that there's quite a lot of application areas in the domain of civil society research where clustering of individuals into things like organizations or repeated records on the same volunteers in different contexts, or the impact of different campaigns or initiative in different contexts. It seems that there's quite a lot of scenarios where data about civil society processes has a natural clustering pattern that might usefully be explored through multi-level models, through random effects multi-level models.
We're going to talk now about estimating and communicating uncertainty. So first of all, let's think about what we mean by uncertainty. We're using uncertainty in a very specific sense here. When we have a sample, we can calculate an average from that sample. We add up all the data, we divide it by the number of observations, we've got an average. That gives us an exact figure. But if what we want to do is to say something about the population outside of our sample, the data that we haven't seen, then we're using our estimate from the sample as an estimate of that population average. An average from a sample is usually a good estimate from a population, but it's not an exact one, and there's some uncertainty around the exact value of the population figure. We've only seen some of the population in our sample. So the data in our sample gives us an estimate of that population average, but it comes with some uncertainty about the exact value. So we're going to think now about how we might measure that uncertainty and also how we might communicate it when presenting our analysis. How much uncertainty there is around an estimate depends on the sample size, how much data we've got in our sample, and also on how variable the thing that we're measuring is. If we're trying to measure something that varies quite widely and is very different between people, then we're going to get less precise estimates than if we're measuring something that is quite similar and just changes a little bit from person to person. And the bigger our sample is, the more data that we have, the more precise an estimate we're going to be able to get of the thing that we're trying to measure. So an estimate that we get from a sample is like our best guess at the population figure. But there's some uncertainty, some range around that figure in which the true value could lie, and we want to be able to quantify that uncertainty and communicate it. The most common way to present uncertainty around an estimate is a confidence interval. So a confidence interval is a range in which we're saying that we think the true value is likely to lie. So instead of just having one figure for our average, we have a range. And we say this range is likely to contain the population figure. The bigger that range is, the more uncertain we are about the value. And the smaller the range, the more certain we are, the smaller the range of possible values. So by showing that range, we give a sense of how uncertain our estimate is and how confident we can be in the estimate of a population value. Let's think about this graphically. Say we're trying to measure average height. We want to know the average height in the population. We can't measure the height of everybody, so we get a random sample of people and we measure their height. And that average in our sample, say, is 147 centimeters. So we can calculate that from the people that we have. We measure all the heights in the sample. But what we want to know is what the population average is. So we're using that average from our sample as an estimate of the average height of people in general. But we've drawn a sample, we haven't seen everybody, so there's some uncertainty around that. And we might measure that uncertainty as being plus or minus 19 centimeters. So that's giving us a sense of a range. So we can see that written down as plus or minus 19 centimeters and also represented on our number line as a range in which we think the population figure might lie. So now rather than just saying the average height in the population is 147 centimeters, we're saying there's a range here in which we think the true value lies. If we have a bigger sample, we're then likely to be able to get a more precise estimate. Our uncertainty is going to be smaller. So perhaps with a bigger sample, we find that our uncertainty is just plus or minus 4 centimeters. So now our range around that value is much tighter. We have less uncertainty. We think that's the range in which the true population average height lies. So we're able to communicate something about the size of that uncertainty. Now we can estimate intervals with different levels of confidence. The most common that we'll see is a 95% confidence interval. And essentially what this means is that the confidence interval we generate will contain the true value about 95% of the time. So we're allowing ourselves to be wrong 1 time in 20. That's our level of confidence. But it would be possible to calculate confidence intervals for other levels of confidence. So for example, we might be more confident to have a 99% confidence interval. But then our interval will be bigger, because in order to be more confident, we have to have a bigger range in which the value could lie. So we're more sure that it's in that range, but the range is bigger. On the other hand, we could be less confident, a 90% confidence interval, and then our interval will be smaller. So we have a smaller range in which we think that the true value will lie, but we're allowing ourselves to be wrong 1 time in 10. So we're going to be wrong more often with the value lying outside that range. So depending on our application, we might have different levels of confidence, but the one that will be most commonly used and you'll see around is a 95% confidence interval. When you see the results of opinion polls in the run-up to a referendum or an election, you'll often see them reported with a 95% confidence interval. So there'll be 35% support for a particular candidate, plus or minus 4%. And that's the confidence interval around that estimate. It gives you some sense of the uncertainty from the estimate. So how do we communicate these differences? We can write down the uncertainty. Common ways to do that are to write our average, 147 centimeters, and then write plus or minus 9 centimeters. That's our confidence interval. Or we can write down the range, so 138 centimeters to 156 centimeters. That's plus or minus 9 from 147. Or we can write that down as an inequality, saying that the average lies between 138 and 156. So we're communicating that range rather than just one number as an estimate. We can also communicate uncertainty graphically. And this is usually done with error bars. So you have a graph, and instead of just showing a point on the graph for the measurement of your average, you show these bars around it. And that's the confidence interval. So that shows the range of that interval. The bigger the bars, the larger the confidence interval, the more uncertain we are about the value of the thing that we're trying to measure. So that communicates the uncertainty visually. Sometimes we're making forecasts into the future, and we want to communicate the uncertainty around those forecasts. And so you'll often see fan diagrams a bit like this one. So the thin purple line on the left shows the measurements that we've made up until today. The vertical dashed line is now, and then we have a projection beyond that. And you can see that that shows a range of values as we go forward in time, and the further into the future, the wider that range is. So there's more and more uncertainty as we go through time. You'll see these sorts of diagrams showing uncertainty around measures of financial variables such as inflation rates, for example. There's a projection into the future, but the uncertainty increases over time. We use uncertainty in particular when we want to make comparisons. We measure 2 averages, say, and we want to be able to tell whether they're different or not. But we know, because we've drawn the sample, that there's going to be some variation in the 2 groups anyway. So how can we tell if that variation is just due to chance or whether it's actually due to there being a difference between 2 different groups? If we quantify the uncertainty around the estimate, then we can get some insight into that. So let's think about one set of measurements. We have 2 groups. We get 2 averages. They're represented by the green dots. And then we have our error bars, our confidence intervals around them. And you can see that those error bars overlap by quite a long way. So that means that the true value of the one on the right could be a bit higher, and the one on the left could be a bit lower. They might be the same. The one on the right might even actually be bigger than the one on the left. So with that much uncertainty and the overlap of those error bars, it's difficult to say that those 2 groups actually have different averages. In another situation, we might have similar 2 measurements, but with a bigger sample size, more precision, and then we have much tighter error bars. And now you can see in the graph on the right that the error bars don't overlap. There's quite a gap between the 2. So that suggests that there is a difference between those 2 groups. that even when you consider the range of plausible values in the two confidence intervals, the estimates are still different from each other. Now that suggests there's a difference between these two groups. And if we compare these two examples, we can see that the estimate of the average is the same. So if you didn't take account of uncertainty, in both cases, you'd have the same numbers and you'd say, yes, there's a difference. But in the case, but once we represent the uncertainty, you can see that in the case on the right, it looks like there is a difference between the two groups. But on the case on the left, there's too much uncertainty for us to be able to draw a conclusion. So estimating and communicating uncertainty is going to be really important when we want to make comparisons of this sort in order to be able to say whether we think there is a real difference or not. So whenever we're trying to generalize beyond data that we actually have in front of us, whenever we want to say something about a population from data that we have on a sample, there's going to be uncertainty. And that comes from the fact that we've drawn a random sample and the composition of that sample might be different from one draw to the next. So it's not going to give us exactly a population figure, but it's going to give us an estimate. It's important to understand and be able to take into account that uncertainty, particularly when we're going to make decisions, when we're going to say things like, these two groups are different from each other, or these two groups are the same. In order to be able to do that, just having the measurement of the average isn't enough. We need to know something about the uncertainty and about whether the range of plausible values overlaps for different groups or not. Now, uncertainty can be a challenging thing to get your head around, and it's just as challenging to communicate to others. Often people want to know what is the number. They want an exact figure, and they'd rather not have a range of plausible values. Hopefully, we've shown here how useful it is to think about the uncertainty in the measurement of data that you're using, and also how important it is to take into account uncertainty when you're making decisions and when you're making comparisons.